All right, what's up, everybody? Welcome back to Structure Free Learning. And today, what we're going to do is do some deflections calculations by double integration method. And just to recall the double integration method, if you covered this already, it starts from the moment curvature relationship, and so many derivations start from the moment curvature relationship. You know, Euler buckling, beam bending, blah 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 blah, right? But so many things from the moment curvature relationship. This is the curvature. This d squared v over dx squared is the curvature of our beam, which is related to the moment divided by ei. And then the double integration method, the idea is that if I integrate twice from the moment function over ei, then I will end up with the deflected shape. And so that first integration would be the slope, this dv dx, that represents the slope, or rise over run, the change in the vertical over the change in the horizontal, is equal to m over ei dx plus a constant of integration that pops out. And then here, the next integral or antiderivative would be this displacement function, the actual displacement of the beam, the deflected shape, based on the moment function divided by ei, the second integral, I guess. Is c1x plus c2. Again, more constants of integration. The challenge here is in this problem is coming up with moment functions and solving for boundary conditions. That's always the biggest challenge, right? And I'm going to give you some tools to help you. So let's do this example problem. Hopefully this will be useful. And what we're given here is a cantilever beam. Let me label stuff. Here's A. We'll call this point B and this point C right here. And what we want to do, we're given that this beam, this thin line right here, has a moment of inertia about its axis, bending about the x-axis of 120 times 10 to the 6 millimeters to the fourth. And the modulus of elasticity is 200 GPa. So it's like a steel I-beam or something. Okay, and the loading here is W equals 1 kilonewton per meter, and that's applied between B and C. And what we want to find are the slope and deflection equations using the double integration method. So the first things first, the way that we're going to solve this is, one, you're going to do some statics. Two, and this is something that maybe not everyone emphasizes, but it's really important, is establishing a coordinate system. Establish coordinate system per moment function. And then you want to come up with moment functions. So you want to actually have moment functions to do the double integration. Moment functions. And then we're going to integrate, or really take antiderivatives, integrate twice. And 5, I know there's a lot of steps, but here, check it out, is boundary conditions. We need to figure out boundary conditions, and then we can finally, after all this, solve, right? And I'm going to tell you right now, probably the most important steps here, or the most important things to understand, is this and this right here. I think you already, from statics, you understand that, and moment functions, and then from calculus, you understand integration. So those are no-brainers compared to everything else that we're about to do. All right, so let's do the first thing. Let's calculate some reactions and make this thing happen. So the first thing we want to do is do our statics. And when I say statics, I'm talking about my reactions here. So here I got an AY, a moment here, MA, and a horizontal AX, which is just 0. Okay, that's 0. I'm not going to even mess around with that. AY, sum of the forces in the Y equal to 0. This going upwards is AY minus 1 kilonewton per meter times 5 meters equal to 0. And that tells me AY is 5 kilonewtons. And then the moment, sum of the moments about A equal to 0. Bam, like this. And here this would tell me that MA minus 1 kilonewton per meter times 5 meters times the arm, which would be 5 plus 2.5, 7.5 meters, is equal to 0. And MA is 37.5 kilonewton meters. All right, so double check my work, but I think that's pretty good. Okay. And if you have questions about the statics, really, you need to review some statics. But here, now, the next thing we want to do is find moment functions. And really, these two steps are combined, okay? But But really, one of the first things we have to figure out is how many moment functions we need, right? So here, 2 is moment functions, and how many do we need? Well, here's how I do it, okay? I look at, it's kind of like shear moment diagrams. I look at how many discontinuities that I have, okay? And a discontinuity is wherever I have a concentrated load. Discontinuity, okay, is a concentrated load or moment to beginnings and ends of distributed loads. And did I have anything else? I can't remember anything else. Shoot. Usually a change in geometry, but that's not going to be an issue here. Changes in geometry. But we don't have that. Okay. Changes in geometry. So here I would have, let's see, my discontinuities, I'll circle in orange, are here at A, the beginning of this distributed load, and the end. And basically I have 3 discontinuities. That means that means I need 2 moment functions, because what I have is in between each discontinuity I need to make a cut and get a moment function for that location, that region right here. So I have 2 moment functions that I need here. And now I know that I have 2 moment functions. I want to establish the coordinate system. I'll call this moment function 1, moment function 2 cut right here. I want to, and I haven't made the cuts yet, but these are the locations. I'm just telling you where, right? Is I gotta establish a coordinate system for each moment function. And for 1 here, I'm gonna choose my x going this way for moment function 1, or between A, B. I'm going to choose my x going left to right here, and my vertical here is V. This is V1 is going to be defined this way. So positive deflection is upwards and negative deflection is downwards. And then for moment function 2, I'm going to define it going right to left with x2 going right here and V2 upwards with 0 being over here. Okay, so this point right here is 0 deflection. V2 going upwards that way. X2 going right to left. All right, so that's important. How we choose the coordinate system really does affect your understanding of this method and getting eventually the correct result, if you will, right here. But so let's go 1 moment function at a time. Let's look at moment function 1. So I'm going to make a cut through 1. So right now I haven't made this cut yet. So let me erase that. Okay, I haven't made this cut yet, but now I'm going to make this cut through 1 and choose either the left or right side of that cut as my free body diagram. It's going to be convenient for me to choose the left side. I could choose the right, but I will choose the left side here just to go. So here we'll say the cut at 1 right here, and my free body diagram for 1 right here looks like this. Here's x1, my V. Here is V1 upwards right here. I have an internal moment, which I will say this is internally positive, M1, which is going to be a function of X, M1. I have a shear and a normal, which really I don't care about. And then here I have my MA, which was 37.5 kilonewton meters, and AY, which was 5 kilonewtons. And so when I solve this out, to get the moment function, I take moments about the cut equal to 0 right here. And here I'll say M1 plus 37.5 kilonewton meters minus 5 kilonewtons times x1 equals 0. Okay? And this M1 as a function of x is 5 kilonewtons times x1 minus 37.5 kilonewton meters. Okay, so that's my moment function for 1. That's my first moment function. I'm going to go and do the same for the next one. So here, this will be the cut through 2, cut at 2. I'm going to choose the right side of my drawing as my free body diagram. So here's my cut. I have the right side of my drawing. I have, well, let me not exaggerate that too much. Here, bam, this location is some distance x2. This was V2 is positive upwards from this being 0. And I have also a uniformly distributed load applied here, and that's also cut. Okay, and this was 1 kilonewton per meter, I believe. All right, and so here again, I have this is my M2, N2, and my V2 going like this. I'm going to take again moments about the cut equal to 0, bam, like this, and I'd have minus M2 minus 1 kilonewton per meter times X, that's the force resultant, times the X2, times X2 divided by 2, which is the arm, okay? And I think that's it, is equal to 0, and that tells me M2 is minus X2 squared over 2 kilonewtons per meter. Yeah, that looks good. Okay, and I think that's it. Shoot, I think that's it for my moment functions. Does that look all right? Yeah. Okay. So hopefully that's good, and I'm not messing this up too much. But here, and now I have my moment functions, and now I can do my double integration. So let's apply that double integration. So here 3 is the double integration. Let's do that, okay? Or which is really 2 antiderivatives, but anyway. So let's do for moment function 1. So for m1 of x1 right here. So, you know, you want to start with the moment curvature relationship. So it'd be like, ooh, not the partial derivative here. It's d squared v1 over dx1 squared is equal to m1 of x1 over ei, okay? Which really is just the moment function, which was m1 is 5 kilonewtons times x1 minus 35.75. Was that right? 37.5. Whoa. Minus 37.5 kilonewton meters times 1 over EI. Okay? And in this case, EI is constant. So I can, you know, just to make this a little bit simpler, I can bring this to this side right here. All right, and just keep this stuff going. So my first antiderivative is the slope. So this would be EI theta, which is the same as EI dv dx right here. And that tells me that I have 5 halves kilonewtons times x1 squared minus 37.5 kilonewton meter times x1 squared plus a constant, and I'll call that C1. Okay, then I take my another antiderivative or integral here. So EIV would just be 6 kilonewtons x1 cubed right here minus 37.5 kilonewton meters divided by 2 times x1 squared plus c1 x1 plus c2. So there's my displacement function. I'll call these ones theta 1 v1 right here. And you know, the units might look weird to you. You have this kilonewton meter squared, but what you got to remember is this EI comes out and is divided by, and the units of EI, if we, you know, we'll just go and calculate real fast. EI is equal to, in this problem, 200 GPa, which is really just kilonewton per millimeter squared, times 120 times 10 to the 6 millimeters to the 4th. And what this does is it's going to give me, you know, 200 times 120 times 10. I don't know what that is. That's some crazy big number. What did you get? 2.4 times 10 to the 10th kilonewton millimeter squared. Okay, that's EI, this constant value right here. And so you can see if I do that, you know, this thing, which makes sense, the slope is going to be dimensionless because this kilonewton length squared divided by EI is going to be a dimensionless quantity, and then EI V1 is going to be this other one. All right, so I'm going to stop here for this part 1, and then we'll resume part 2 in the next video.